there is a question that lives inside every enormous wave, one that sailors have turned over in their minds for as long as people have crossed open water. Not just how dangerous is this wave, or how do I survive it, but something more fundamental. How big can a wave actually get before the ocean itself refuses to let it grow any taller? That question sounds simple. It turns out to be one of the most contested, surprising, and genuinely unsettled problems in ocean science. And the answer depends almost entirely on what kind of wave you're talking about, and how you measured it. A buoy anchored off the coast of Newfoundland recorded a single wave taller than 30 meters during the remnants of Tropical Storm Dorian in September 2019. That is roughly the height of a 10-story building moving through open ocean. A satellite operated by the European Space Agency captured a wave of nearly 20 meters from orbit in December 2024, and during that same storm, individual crests reportedly exceeded 35 meters. A big wave surfer named Sebastian Draupner dropped down a wall of water at Nazaré, Portugal in early 2024 that drone measurements placed at nearly 29 meters, a potential world record still awaiting official ratification. And then there is the outlier that makes all of those numbers look modest, a landslide in Lituya Bay, Alaska in 1958 that sent a wave surging 524 meters up the opposite hillside, stripping trees from the slope like they were never there. Those four events involve four completely different kinds of waves. A buoy measured rogue wave, a satellite snapshot of a storm swell, a surfed wall of water shaped by a canyon on the seafloor, a mega tsunami born not from wind, not from storm, but from 10 million tons of rock dropping into an enclosed bay. Calling them all waves is a bit like calling a campfire and a volcanic eruption both fire. Technically accurate, practically misleading. That is the first thing this video is going to untangle. What we actually mean when we say biggest wave, because the definition changes the record, and the measurement method can shift the number by several meters in either direction. But there is a deeper tension here, one that runs through the entire history of humanity's relationship with the ocean. For centuries, sailors came back from deep water crossings with stories of walls of water that appeared from nowhere, towering above the masts of ships that had no business surviving them. Waves that dwarfed everything the surrounding sea had produced minutes before. Waves that should not have existed according to the models oceanographers were using at the time. Scientists mostly did not believe them. The instrument said those waves were impossible. The physics said they were impossible. The statistical models said a wave that large, in those conditions, should occur so rarely that no living sailor could expect to see one. And so the stories were catalogued somewhere between exaggeration and myth, the kind of thing exhausted men see after weeks alone on a heaving deck. Then, on New Year's Day, 1995, a single measurement from an oil platform in the North Sea rewrote the conversation permanently. That is the turn this video traces, from dismissal to documentation, from folklore to instruments, from gut-level dread to verified data. Along the way, we're going to follow how wind energy builds a wave from nothing, how physics eventually draws a hard line on how steep a wave can become before it collapses under its own geometry, and why even with that theoretical ceiling sitting somewhere near 30 meters, the ocean still finds ways to produce waves that push right against it. We're going to look at the distinction between a storm wave, the kind that builds steadily as wind blows across thousands of miles of open water, and a rogue wave, which is something categorically different, an anomaly, a statistical outlier, a wave that appears in seas where it has no mathematical right to exist. We're going to watch big wave surfers treat those same 30-meter walls as something to be ridden rather than feared, and we're going to look at the ships that took direct hits from rogue waves and somehow stayed afloat, and the ones that did not. And at the far end of the scale, we are going to stand at the edge of Lituya Bay and try to understand what it means that the largest wave ever recorded was not generated by any storm at all. The answers here are not clean. Wave height figures shift depending on whether you are measuring crest to trough on a single wave or averaging across a statistical set. Satellite snapshots, buoy accelerometers, and drone photogrammetry all produce slightly different numbers, and the gaps between measurements sometimes hide the actual peak entirely. A buoy only transmits 10 minutes of data every hour. A lot can happen in the other 50. What we do know is that the ocean is larger and stranger, and in some ways more extreme than the models once allowed. The question of how big a wave can get has been getting a bigger answer every decade, and the question of whether a person can survive one turns out to have a more complicated answer than either fear or bravado would suggest. Before we can argue about which wave holds the record, we need to agree on what we are actually measuring, because that turns out to be a surprisingly complicated negotiation between scientists, sailors, satellite engineers, and professional surfers, and none of them are using quite the same ruler. Start with the most basic unit. A single wave height is measured from trough to crest, the vertical distance between the lowest point in the valley behind a wave and the highest point at its peak. That sounds unambiguous until you realize the ocean is never producing just one wave. It is producing hundreds of overlapping wave trains simultaneously, each moving at a different speed and direction, all adding and subtracting from one another in constantly shifting combinations. At any given moment, the surface is not a clean series of crests. It is a chaotic, three-dimensional landscape that rises and collapses faster than any single observer can track, so oceanographers developed a statistical shorthand. They call it significant wave height, and it is the term you will encounter in almost every scientific paper on ocean conditions, every weather forecast issued to shipping, and every instrument reading radioed back from a data buoy. Significant wave height, abbreviated as SWH, is defined as the average crest-to-trough height of the highest one-third of waves recorded over a given time window, typically around 20 minutes. There is also an equivalent mathematical definition that calculates it as 4 times the standard deviation of the sea surface elevation, which produces nearly the same number through a different route. Either way, significant wave height is not describing any single wave. It is describing the statistical character of an entire sea state. That distinction matters enormously when headlines start attaching record labels to numbers. A storm that produces a significant wave height of 15 meters is a violent, life-threatening sea, but individual crests within that storm will routinely exceed the significant wave height figure. Roughly one wave in every 1,000 or so will be more than twice the significant wave height of the surrounding sea, which is incidentally one of the rough thresholds used to define a rogue wave, understanding that single peak is what most record claims are actually chasing. When you read that the largest wave ever measured reached 30.2 meters, that number refers to one specific crest-to-trough measurement of one individual wave, not an average across any set. The distinction between that number and the significant wave height of the surrounding sea at the same moment can easily be 10 or 15 meters. Now add the question of who or what is doing the measuring, because that changes the number too. A moored ocean buoy does something remarkably straightforward. It bobs. An accelerometer inside tracks its vertical motion continuously, logging the full-time series of wave heights in real time. Because the record is continuous, a buoy will catch a single exceptional wave the moment it passes through. When a buoy anchored off the coast of Newfoundland registered a 30.2 meter wave on the 8th of September, 2019 during the remnants of Tropical Storm Dorian, that number came from exactly that kind of uninterrupted local record. The instrument was there, the wave passed directly under it, and the crest-to-trough measurement was logged at the moment of occurrence. that is as close to a clean individual wave record as ocean science currently produces. A satellite operates on completely different logic. An instrument like the Poseidon 3C altimeter on the SWAT satellite fires pulses of radar downward and measures the time it takes for them to bounce back from the sea surface, inferring wave height from the spread and texture of the return signal. But that return signal is averaged over a footprint that can stretch across 50 kilometers of ocean. The 19.7 meter significant wave height that SWAT recorded on the 21st of December 2024, the highest value ever captured by a satellite instrument, is a statistically average number across a broad swath of sea, not the height of any single crest. It is entirely possible, and in fact quite likely, that individual waves within that same patch of ocean exceeded the satellite's figure significantly. The satellite simply cannot resolve down to a single wave. It gives you a rigorous, globally consistent measurement of the sea state, which is enormously valuable for climate science, wave modelling and shipping safety. But it is measuring something categorically different from what the buoy off Newfoundland captured. Both numbers are valid. They are answering different questions. Then there are surfer records which operate in a third entirely separate domain. Big wave surfing has its own governing bodies, its own record categories, and its own measurement methodology, and it has no formal relationship with oceanographic data collection. For most of surfing's history, wave heights were estimated visually, by observers on the shore, by fellow surfers in the water, or by the judgment of a panel reviewing footage. Those estimates varied wildly. Different measuring conventions competed with each other. Some traditions measured waves from the back face rather than the front, producing numbers that were consistently and sometimes dramatically smaller than the crest-to-trough figure a scientist would calculate. The results were comparisons that made no sense, records that could not be verified, and a persistent credibility gap around the very largest claimed rides. Drone photogrammetry has started to close that gap. When Sebastian Steudtner rode a wave at Nazaré, Portugal in February 2024, and a drone-based measurement system calculated the height at 28.57 meters, roughly 94 feet, that number came from high-resolution aerial imagery processed through photogrammetric software that can reconstruct the three-dimensional geometry of the wave with far more precision than any human eye. It is meaningfully more reliable than a visual estimate. But the method is still being standardized. Different processing approaches can produce slightly different outputs, and the measurement was still pending official ratification at the time it was reported. That is not a criticism of the technology or the athlete. It is simply an honest acknowledgement that surfing records exist in their own verification pipeline, one that is distinct from oceanographic measurement and still maturing. The deeper problem that drone photogrammetry is trying to solve is the old problem of visual estimates, and it is worth pausing on that for a moment because visual estimates are where most of history's largest wave claims live. For centuries, the only record of an extreme wave was a sailor's account of what they saw from a heaving deck in the middle of a storm, often at night, usually in conditions that made precise observation impossible and survival the only priority. Those accounts are often vivid. They are sometimes internally consistent and corroborated by multiple witnesses. They are almost never scientifically verifiable. The height of a wave looks different depending on where you're standing relative to it, how experienced your eye is, how frightened you are, and whether you are at the crest of the preceding wave or deep in its trough when the face of the next one rises in front of you. The same wave can look twice as tall from the bottom of a trough as it does from an elevated vantage point. Without an instrument logging the sea surface elevation continuously and independently, there is no ground truth to compare the story against. Modern verification matters because the stakes of getting this wrong extend well beyond bragging rights. If the models that predict maximum wave heights are calibrated on records that are inflated by visual exaggeration, The engineering standards for ships and offshore platforms may be set to the wrong tolerances, in either direction. If verified measurements keep pushing the documented upper limit higher, the models need to follow. The transition from anecdote to instrument is not just an academic preference. It is the difference between a standard that protects lives and one that merely sounds reassuring. So here is where that leaves the record landscape, which is genuinely plural and genuinely messy, in ways that the rest of this video will keep running into. The highest significant wave height ever measured from space is 19.7 meters, captured by a satellite altimeter in December 2024. The largest individual wave ever measured by a continuous buoy record is 30.2 meters, logged off Newfoundland in September 2019. The largest wave ever officially attributed to a surfer, pending final ratification, was measured by drone at 28.57 meters in February 2024. And looming over all of those figures is a completely separate category, the mega tsunami, generated not by wind or storm but by geology, a category where the numbers do not just break the scale, they shatter it. Each of those records is legitimate. Each is the largest of its specific type under its specific measurement methodology. None of them contradicts the others. The confusion comes from treating them as if they belong to a single ranked list, which they do not. A satellite averaged over 50 kilometers of ocean, and a buoy logging one extraordinary crest are both measuring waves. They're not measuring the same thing the same way, and conflating them is how you end up arguing about records that were never actually competing. Keep those definitions in your pocket. The rest of this story is going to need them. So now that we know what we're measuring and how those measurements can diverge, the next question is where these waves actually come from, and why some of them end up so much larger than others. The short answer is wind. But wind is not a simple input with a predictable output. It is a variable that interacts with two other variables simultaneously, and the relationship between the three is what separates an ordinary choppy afternoon on a bay from a 40-foot open ocean swell that has been travelling for days. Those three variables are wind speed, duration, and fetch, and you need all of them working together in the same direction at the same time to build a genuinely large wave. Fetch is the one that surprises people most. It is the uninterrupted distance over which the wind is blowing across the water surface. If the wind is blowing at 50 knots but only has 2 miles of open water to work with before hitting a shoreline, the waves it can build are strictly limited. The water surface simply has not been exposed to the wind long enough for energy to accumulate. But give that same 50-knot wind 1,000 miles of open ocean, running in the same direction, and the situation changes entirely. The wave field has time and space to develop, grow, and organize. The relationship between wind speed and wave height is not linear. It scales with the square of wind speed. The classical deep-water formula for fully developed seas, developed from decades of oceanographic measurement, expresses significant wave height as roughly proportional to wind speed squared, divided by gravitational acceleration. What that means practically is that doubling the wind speed does not double the potential wave height, it quadruples it. A storm that intensifies from modest to severe is not producing twice the waves. It is producing a fundamentally different sea state. But that potential only gets realized if the fetch is long enough and the wind blows long enough for the waves to actually catch up to the full energy the wind is capable of delivering. The mechanism of energy transfer starts at the surface. Sustained wind creates pressure variations and friction against the water, disturbing it into small ripples almost immediately. Those ripples increase the surface area available for the wind to push against, which accelerates energy transfer, which builds the ripples into wavelets, which build into organized waves. As the waves grow, they start traveling in the same direction as the wind that made them. Eventually, some waves approach the speed of the wind itself, and at that point they can no longer absorb additional energy efficiently. The sea has become fully developed for those conditions. When the storm moves on or the wind drops, something remarkable happens. The waves it generated do not simply stop. They decouple from the wind that created them and reorganize into swell. Long, smooth, coherent trains of energy traveling outward in all directions from the storm center. Long period swell, with wave periods of 12 to 20 seconds between crests, can travel at 60 to 100 kilometers per hour. It can maintain most of its energy across 1,500 kilometers or more. A winter storm that hammers the North Atlantic doesn't just affect the ships that sail through it. Its swell arrives on coastlines days later, sometimes on the other side of an ocean basin. Surfing communities actually track this. A powerful swell generated near New Zealand in 2022 was traced all the way to Chile, more than 11,000 kilometers away, arriving coherent enough to still be worth riding. Now consider what the open ocean provides that enclosed bodies of water cannot. Fetch in the thousands of kilometers, no interrupting land masses, no sudden shallowing that would rob energy from the wave base. Deep water means waves can grow to their full, unimpeded height without dragging on the bottom. This is why the most extreme wave heights on record, the ones that end up in scientific papers and in the stories we'll be looking at later in this video, tend to come from specific regions of ocean that happen to be wide open downwind of powerful storm tracks. The Southern Ocean, the high-latitude North Atlantic, the far North Pacific. These are places where storms have room to run, and the waves they generate have room to grow. Not all parts of a storm are equally productive, and this is where the physics becomes genuinely counterintuitive. An extratropical cyclone, the kind of massive, slow-rotating pressure system responsible for the most violent mid-ocean conditions, does not produce the same wave heights in every direction. The right rear quadrant of a fast-moving storm in the Northern Hemisphere is typically where wave heights peak, sometimes dramatically. The reason is that in that sector, the storm's forward motion adds to the wind speed relative to the wave field, and, critically, the waves stay under wind, forcing for longer. They travel in roughly the same direction the storm is moving, which means the storm keeps pushing them. The effective fetch is extended far beyond what the physical size of the storm would suggest. In powerful extratropical cyclones with center wind speeds of 26 to 34 meters per second, research has shown that significant wave heights in this favored sector can exceed 10 meters in the surrounding sea state, and can run as much as 10 meters higher than the opposite side of the same storm. The same pressure system, the same moment, and you can be looking at sea states that differ by the height of a 3-story building depending purely on where you're relative to the center. That asymmetry is not academic. It explains why two ships separated by 50 miles in the same storm can report completely different conditions. It explains why wave buoys in what looks like the same weather event can log vastly different maximum heights. It explains why storm hindcast models, which try to reconstruct historical sea states from atmospheric records, can differ from one another by 10 to 20%, depending on which empirical formulas they rely on for fetch duration growth. Those formulas are calibrated from real data, but they're not identical, and real oceans are messier than any model assumes. What all of this builds toward is the recognition that large waves are not random events. They are the product of a specific convergence, enough wind speed, sustained long enough, over enough unobstructed open water in the right sector of a powerful storm system. When those conditions align, the ocean organizes itself into swells of extraordinary height and period that can travel halfway around the world without losing their fundamental structure. The mechanics are well understood, and the growth is constrained by real physical limits that we'll come to shortly. But here's the thing about understood mechanics and physical limits. They describe the average behaviour of a storm-generated sea. They account for what wind and fetch and duration can build under the laws of fluid dynamics. What they do not fully account for, what took oceanographers entirely by surprise and required a dramatic event on New Year's Day in 1995 to finally prove, is what can happen when wave trains from different directions arrive at the same place at the same time. Because when that happens, the rules of ordinary storm physics stop being sufficient. So the previous section ended with a constraint, the recognition that wave growth is not unlimited, that real physical limits govern how tall a wind-generated wave can get before physics intervenes. Let's examine exactly where that limit is drawn and why it exists. Every wave moving across deep water is characterized by two dimensions that matter most: its height, meaning the vertical distance from trough to crest, and its wavelength, the horizontal distance from one crest to the next. These two dimensions are not independent. They are linked by a ratio, and that ratio has a hard ceiling. The ceiling is called the Misha criterion. What it states, in precise terms, is that the ratio of a wave's height to its wavelength cannot exceed approximately 0.142 before the wave becomes structurally unstable and breaks. That number comes from the mathematics of periodic wave motion in deep water. It is not an empirical approximation derived from watching waves and guessing, but a result that falls directly out of the underlying equations governing how water moves. If you try to push a wave beyond that ratio, its crest becomes too steep. The water at the top can no longer sustain its position, and the wave breaks. The steepness limit acts as a hard geometric constraint on what a wave can be. To understand what 0.142 means in plain language, think about it this way. Take the height of a wave and compare it to the distance between one crest and the next. If that height is more than roughly 1/7 of the distance between crests, the wave is going to break. 1/7 is not a large fraction. It means that even an enormous, powerful ocean wave is, relative to its own length, a surprisingly flat structure. A wave with a crest-to-crest distance of 100 meters can be no taller than about 14 meters without breaking. A wave with a crest-to-crest distance of 50 meters is already unstable above 7 meters. The wave can be wide without being proportionally tall, but it cannot be tall without being proportionally wide. This is where the wavelength of ocean waves becomes the key variable. In deep water, the relationship between a wave's wavelength and its period, the time between successive crests passing a fixed point, is governed by a well-established equation from fluid mechanics. Wavelength equals the gravitational acceleration multiplied by the square of the period divided by 2 pi. Run the numbers for a typical period at the extreme end of what wind-generated storms produce, around 12 seconds, and you get a wavelength of roughly 225 meters. Apply the Mishi ratio to that. 0.142 multiplied by 225 meters gives you a theoretical height ceiling of about 32 meters. Round it to practical terms and you arrive at the commonly cited figure of approximately 30 meters as the realistic deep water upper bound for wind-generated waves. That figure deserves some scrutiny. The most extreme wind-sea periods, those approaching and exceeding 12 seconds, require storms of extraordinary intensity with hundreds of kilometers of fetch. Even at those periods, the Mish limit is a ceiling on what a wave of that wavelength can structurally sustain before breaking, not a guarantee that waves will actually reach that height. In reality, the constraints of wind speed, fetch, and storm duration typically keep observed waves well below this theoretical maximum. The 30.2 meter wave recorded by a buoy off Newfoundland in September 2019, one of the largest individual waves ever instrumentally measured, was already sitting at the edge of what the steepness criterion permits for those wavelengths. It was not merely a record, It was a wave pressing against the boundary of what physics allows while remaining coherent. There is an important distinction between what the Misch criterion describes and what real storm seas actually produce. The criterion applies to a periodic wave, a mathematically regular, idealized structure moving through open water without interference from other waves, without underlying currents, and in uniform depth. Real ocean conditions are none of those things. Ocean waves travel in groups rather than as isolated entities. They interact with currents that can compress or stretch their wavelengths. They encounter shallow areas where the bottom changes the dynamics entirely. In any of those scenarios, a wave can break at a steepness lower than 0.142, because the instability threshold can be triggered by factors beyond pure geometry. The Mischy number sets the absolute upper bound. Real oceans often enforce a lower effective ceiling. This is why oceanographers studying extreme wave events tend to treat the 30-meter figure as a practical ceiling rather than a reliable prediction, and why the 2019 Newfoundland measurement attracted the attention it did, not just for its absolute height, but for how close it sat to a limit most scientists assumed would rarely be approached. This also explains something intuitive about wave behavior that becomes more striking the more you think about it. A wave cannot grow indefinitely taller simply because more energy is being put into the sea. At some point, adding more energy does not produce a taller, coherent wave. It produces a breaking wave that dissipates much of that energy as turbulence and white water. The breaking itself is the ocean's mechanism for releasing energy that the wave structure can no longer contain. The steepness limit is not just a description of when waves break. It is the reason why the ocean cannot produce wind-driven waves of arbitrary height no matter how violent the storm. Now, that last sentence requires one careful qualification, because it applies only to the category of waves we have been discussing so far. Wind-generated gravity waves, driven by atmospheric energy transferred to the surface through friction and pressure variations. The physics governing these waves and the steepness constraint that caps them depends on the relationship between wave height and wavelength in a regime where wavelengths are measured in hundreds of meters and periods in tens of seconds. There is another category of wave that does not belong to this regime at all. Landslide-generated megatsunamis, and to a lesser extent seismically triggered tsunamis, operate with wavelengths not in the hundreds of meters, but in the hundreds of kilometers. The dynamics that produce them, the sudden displacement of enormous volumes of water by a submarine landslide or a fault rupture, are entirely different from the wind-sea growth process. And because their wavelengths are so vastly larger, the Misch criterion simply does not apply in the same way. You cannot use the 1/7 ratio derived for wind waves to set an upper bound on what a landslide into a bay can produce, because you are dealing with a different physical regime altogether. The number that will appear later in this story, 524 meters, does not violate any law of physics. It was just produced by a mechanism that wind and fetch and storm duration have no part in, and belongs in a fundamentally separate category from anything the Misch criterion was designed to describe. But before we reach that outlier, there is a category of wave that sits squarely within the wind-sea world, and that exceeded the Misch limit in a different sense, not by breaking the steepness constraint, but by appearing at heights that seemed physically impossible given the surrounding sea state. Waves that sailors had been reporting for decades. Waves that scientists had dismissed as exaggeration. And then, on New Year's Day in 1995, a single platform off the coast of Norway measured one in real time. For centuries they came back from the sea with the same story. A wave unlike the others. Not a larger version of the swell surrounding it, but something qualitatively different. A vertical wall of water appearing with little or no warning, rising far above the mast, blotting out the horizon, and hitting with a force that bent steel and buckled hulls, designed to withstand the worst the North Atlantic could produce. The sailors who survived described it in terms that sounded to anyone who had not seen it like the product of fear and darkness and an overactive imagination. Science, for most of its modern history, agreed with that assessment. In 1826, the French explorer Jules Dumont d'Urville returned from an ocean voyage and reported encountering waves he estimated at up to 33 meters, roughly 108 feet, in height. The claim was presented not as casual anecdote, but as an observation from an experienced navigator with scientific training. The response from the French Academy of Sciences was swift and dismissive. The physicist François Arago essentially told d'Urville that the figure was impossible, that the physics of wave formation simply did not permit waves of that height, and that the account should not be taken seriously as data. D'Urville had sailed across the ocean and returned with eyewitness testimony. Arago had the mathematical models. The models won. This pattern repeated itself throughout the 19th and 20th centuries with remarkable consistency. Ship logs from vessels crossing the North Atlantic, the Southern Ocean, and the waters around the Cape of Good Hope accumulated accounts of monstrous single waves emerging from otherwise survivable sea states. In 1910, the RMS Lusitania, not yet famous for the manner of its eventual end, was struck by a wave estimated at 23 meters while crossing the Atlantic. The MS München, a German cargo ship lost in 1978, went down in the North Atlantic under conditions that left investigators examining its wreckage for an explanation. What they found was structural damage to metal components mounted more than 20 meters above the waterline, damage consistent with a wave exceeding that height hitting the vessel. The ship was gone, the crew was gone, and the physical evidence pointed towards something that the official model said could not exist. Investigators filed their reports. Scientists noted the findings. The models were not revised. The reason the models were so resistant to revision comes down to a statistical assumption that was, for calm seas and average conditions, entirely reasonable, and for extreme events, catastrophically wrong. Oceanographers had long described the distribution of wave heights in a sea state using what is called a Rayleigh distribution, a bell curve-shaped model in which wave heights cluster around the significant wave height, which itself is defined as the average of the highest one-third of waves in a given period. Under this model, the probability of a wave substantially exceeding the significant wave height drops off sharply. You can calculate exact odds. Run the numbers for a wave more than twice the significant wave height of a given sea state, and the Rayleigh distribution tells you it should occur, statistically, roughly once in every 10,000 years, n. Not once per decade on a particular shipping route, not once per year across the entire global ocean, once in 10,000 years. The problem is that the actual ocean produces such waves with a frequency that bears no resemblance to that figure. Sailors were not encountering 10,000-year events on a routine basis. What was happening was something the Rayleigh distribution was not built to capture, a sea state in which wave heights, under certain conditions, do not follow a tidy bell curve at all. The real distribution has a heavier tail than the model assumes. Extreme events are not just possible, they are meaningfully more probable than the mathematics suggested, and in certain oceanographic conditions, they are actively concentrated rather than randomly dispersed across the probability curve. But pointing that out required data, and the data that existed was almost entirely anecdotal. Visual estimates of wave height from a ship in distress carry an inherent uncertainty that can run to 10% or more in either direction, and that is under ideal observing conditions, which a vessel in a severe storm emphatically does not provide. There was no instrument record. There was no laser rangefinder mounted on a stable platform, sampling the water surface continuously and storing the measurements for later analysis. There were only sailors, and sailors, the scientific consensus had decided, were not to be trusted on this particular subject. The consequences of that dismissal went beyond a failure of intellectual humility. They had direct practical implications for the engineering of ships and offshore structures. If the models said extreme single waves were effectively impossible, then the structures placed in the ocean did not need to be designed to withstand them. A typical breaking wave of around 12 meters can strike a hull with a force of approximately 6 tons per square meter. A rogue wave can generate forces exceeding 100 tons per square meter, more than 16 times greater. These are not forces that differ in degree from the baseline design assumption, they differ in kind. A structure built to survive standard storm loads and encounter a genuine rogue wave is encountering something its designers explicitly decided not to account for, on the basis of a statistical model that said they would never need to. In September 2000, the British research vessel RS Discovery was operating in the North Atlantic west of Scotland when instruments aboard recorded a crest-to-trough wave height of 29 metres. Post-event analysis revealed something particularly telling. Every weather forecast and wave model running at the time had failed to predict it, not underestimated it, failed entirely to suggest that a wave of anywhere near that magnitude was possible in the prevailing conditions. The models had looked at the wind speed, the fetch, the storm track and the sea state, and they had not seen it coming. The RRS Discovery had no choice but to see it coming, because it was already there. That event deepened the unease that had been quietly building among oceanographers, who had begun to suspect the Rayleigh distribution was telling them a story that the ocean was not actually telling. But the RRS Discovery wave, as striking as it was, remained a single data point from a research vessel that survived to report it. The real turning point had come 5 years earlier, on the first day of a new year, from a gas platform standing in the North Sea, equipped with a downward-pointing laser that had been measuring the surface of the water all along. January 1, 1995. The Draupner platform sat in the North Sea approximately 160 kilometres off the coast of Norway, an unmanned gas installation doing what unmanned gas installations do: collecting data, processing it, transmitting it, with no crew aboard to feel the storm that was moving through the area that New Year's Day. A laser rangefinder mounted on the platform pointed straight down at the water surface below, sampling the distance between itself and whatever the North Sea was doing at that moment, continuously, without interruption, without the filtering effect of human perception, trying to make sense of chaos. It was not looking for anything unusual. It was simply measuring. At approximately 3:20 in the afternoon, it measured something that would take years to fully understand. The laser recorded a wave with a crest-to-trough height of 25.6 meters, just over 84 feet. That number alone would have been remarkable, but what made it scientifically extraordinary was the context surrounding it. In the 20 minutes during which that wave appeared, the significant wave height, the average of the highest third of all waves in that period, was approximately 12 meters. The Draupner wave did not rise 25.6 meters above the ocean floor. It rose 25.6 meters from trough to crest, within a sea state, in which the typical large wave was reaching 12 meters. It was more than twice the height of the surrounding seas. It was not a big wave in a big storm. It was an outlier so extreme that the statistical framework governing how scientists understood wave distributions had no honest way to account for it. The Rayleigh distribution, as described in the events leading up to this moment, was not merely strained by this finding, it was broken by it. Under Gaussian wave statistics, a wave of this magnitude relative to its surrounding sea state should occur roughly once every 10,000 years. That is not a figure expressing caution or conservatism. It is a figure expressing practical impossibility. And yet here it was, time-stamped and laser-measured, corroborated not by a frightened sailor's estimate from a heaving deck in the dark, but by multiple simultaneous instruments on the platform itself, pressure sensors, acceleration sensors, tension readings in the platform's mooring structure, all of them recording in their different ways the passage of exactly the event the laser had captured. The Draupner wave had witnesses, and those witnesses were machines that did not embellish, did not misremember, and did not care whether the result was convenient. This was the difference that everything had been waiting for. Every wave account before Draupner, D'Urville's 33-metre estimate, the damage to the München superstructure, the testimony of uncountable mariners, had the fatal weakness of being a human observation in difficult conditions. However compelling the accumulation of those accounts, however obvious the pattern they described, the scientific community had a legitimate methodological objection. The data was soft. Eyewitness evidence is uncertain evidence. Models built on mathematical principles outranked stories, and so the stories had been set aside. The laser on the Draupner platform produced hard data. It produced a number, a timestamp, and a sea state context, all simultaneously recorded, all retrievable, all checkable. It produced for the first time the one thing the scientific argument against rogue waves had never had to answer: direct instrumented proof. There was no longer a debate about whether monster waves existed. There was only the question of what to do now that they had been confirmed. What scientists did was begin the uncomfortable process of revising everything downstream from that statistical assumption. The implications spread in multiple directions at once. Post-event analysis using nonlinear wave models, models that account for the way waves interact with each other in ways that amplify rather than average out, showed that the probability of a Draupner scale event is not 1 in 10,000 years. Depending on the model and the conditions, the probability of such a wave occurring in a given sea state could be as high as around 13% under certain nonlinear statistical frameworks, compared to roughly 0.5% under the old Gaussian model. That is not a refinement of the estimate. That is a fundamental change in the underlying physics being applied, with a 26-fold difference in the resulting probability. For offshore engineers, this was immediately and practically alarming. Platforms, oil rigs, and ship hulls had been designed using load calculations derived from wave statistics that, it now appeared, had been underestimating the probability of extreme events by an order of magnitude or more. The force a rogue wave generates on a structure is not proportionate to its height. It scales in ways that can exceed the design tolerances of vessels and platforms built according to the best available models of the 1970s and 1980s. The Draupner wave did not sink the Draupner platform, which was fortunate and also somewhat beside the point. The platform was an unmanned industrial installation built with significant structural margins. A cargo ship or a passenger liner encountering the same wave in the same sea state would have faced a very different outcome. The risk models had not accounted for that. They now had to. Beyond the engineering implications, Draupner changed what scientists were looking for. The monster wave was no longer a category of event that could be rationalized away. It was a documented physical phenomenon with a confirmed statistical signature, and that meant it needed to be understood, predicted, and ultimately detected before impact, rather than measured in the wreckage afterward. The Draupner event became the reference point for an entirely new research direction, not simply studying large waves as extensions of normal wave distributions, but studying extreme outliers as a distinct class requiring distinct models, distinct observational systems, and distinct hazard assessments. This distinction matters, and it is worth being precise about it. A rogue wave is not simply a large wave in a large storm. It's a wave that rises dramatically above the significant wave height of its surrounding sea state, conventionally defined as exceeding twice that value. The Draupner wave, at more than double the surrounding significant wave height, met that definition with room to spare. A 12-metre wave in a sea state where the significant wave height is also 12 metres is an unremarkable swell. A 25.6-metre wave in a sea state where the significant wave height is 12 metres is something categorically different, something that demands a different vocabulary, a different mathematical treatment, and, as events would show, a serious and sustained effort to build the tools capable of finding such waves before they find us. The laser on the Draupner platform had not been installed to hunt for monsters, but by measuring one, it forced an entire scientific field to start doing exactly that. The Draupner measurement did not resolve the problem, it defined it. Once scientists understood that rogue waves were real, statistically significant, and capable of appearing without warning in open ocean conditions, the obvious next question was equally obvious in its inadequacy. How many times had this already happened without anyone knowing? The laser on that North Sea platform had been in the right place at the right moment almost by accident. The ocean covers 361 million square kilometres. One platform, one storm, one New Year's afternoon was not a monitoring network. It was a single data point with enormous implications and nowhere near enough company. The hunt required instruments. Fortunately, the groundwork had already been laid, piece by piece, across the preceding decades, not specifically to chase extreme waves, but to understand ocean conditions more generally. What Draupner did was give that existing infrastructure an urgent new purpose. Start with the buoys. The United States National Data Buoy Center had been expanding its network of moored ocean buoys since the 1970s, and through the 1980s it undertook significant upgrades, improved hull designs that reduced noise from the buoy's own motion, and better algorithms that corrected for the dynamic response of sensors being thrown around in rough seas. The result was a system capable of measuring significant wave height to within about 0.2 metres in 95% of recorded cases. That sounds like a modest technical achievement, but what it actually meant was this. You now had instruments anchored at fixed points across the ocean, recording the complete wave spectrum continuously, 24 hours a day, in every sea state from flat calm to full hurricane. Not passing ships, not human observers trying to estimate wave heights from a heaving deck, not infrequent research cruises sampling conditions at convenient intervals. Continuous time series data, logging every wave, every hour, every year. That continuity is the critical factor, and it is worth dwelling on why. A ship passing through a storm captures a snapshot. Conditions as they were during transit, filtered through the perception and judgment of whoever was watching. A moored buoy captures the full sequence of events, from the first swell of an approaching storm to its peak intensity to the gradual return to baseline. When an extreme wave appears in that record, it appears with complete statistical context. What the sea state was before it, during it, and after it. That context is what makes the data scientifically usable. The Draupner wave was significant precisely because it came with exactly this kind of contextual envelope. Expanding the buoy network meant replicating that capacity across ocean basins where previously only guesswork and logbook anecdotes had existed. Coastal radars added a different layer. High-frequency radar systems, the technology known as CODAR, were developed through the mid-1980s and can infer directional wave spectra by analysing the way radio signals scatter off the sea surface. They deliver wave height estimates with an uncertainty of around 5% and can map wave conditions across ranges of 30 to 60 kilometres from the antenna. They do not replace in situ sensors, and they come with their own blind zones near the antenna and their own systematic errors that need careful calibration. but they offer quasi-continuous coverage over spatial scales that no buoy network can economically match, which means that in coastally monitored regions, a large wave propagating shoreward leaves a trackable signature rather than a sudden surprise. Offshore platforms provided yet another measurement pathway. The Draupner installation had proven that a fixed structure fitted with a downward-looking rangefinder could capture extreme events with precision and with the additional corroborating data that comes from having multiple simultaneous sensors in the same location. The offshore oil and gas industry had strong commercial reasons to monitor wave conditions around its infrastructure, and as the post-Draupner awareness of rogue wave risk filtered through engineering and safety communities, the instrumentation of platforms became both more common and more sophisticated. The cumulative effect of all this, the upgraded buoy networks, the coastal radar arrays, the instrumented offshore structures, was not simply more data. It was a fundamentally different relationship between scientists and the ocean's extreme events. Before these systems, extreme waves were things that happened to people, and occasionally to platforms in ways that could be measured after the fact, in damage surveys and distress calls. Afterward, they became things that could be observed in real time, logged with precision, and analysed within a statistical framework that did not depend on anyone's eyewitness account. And what the data showed was unsettling in a specific way. The long-term records that accumulated through the 1990s and 2000s began making clear that waves exceeding 25 metres were not once-in-10,000-years events. They were occurring multiple times per decade in storm-prone ocean basins. The probability estimates that had seemed conservative when they were derived from ship logs now looked not just wrong, but drastically, systematically wrong. The product of an observational system with enormous blind spots rather than an accurate picture of a mostly docile ocean that occasionally surprised itself. This matters because the stakes attached to those probability estimates were not abstract. Ship hulls, offshore platform designs, and structural load calculations had been built to withstand wave forces consistent with the old statistics. Revising the frequency upward did not require redesigning the entire global fleet overnight, but it did require an honest reckoning with the gap between designed tolerance and encountered reality. Into this context came the event that put a specific number on the new measurement era's capabilities. On September 8, 2019, a buoy positioned roughly 2.5 kilometres off Porto Basque, Newfoundland, was in the path of post-tropical storm Dorian. The buoy was doing what buoys do, recording continuously without interpretation or alarm, when it captured a single wave with a crest-to-trough height of 30.2 metres. That is almost exactly 99 feet. It remains the tallest wind-generated wave ever documented by any in-situ sensor anywhere on the ocean's surface. The number matters, but so does the mechanism that produced it. That measurement did not exist because Dorian was unprecedented. It existed because a well-calibrated instrument with continuous sampling was anchored in the right location when the storm passed through. The wave almost certainly was not the first wave of that height ever generated in the North Atlantic. It was very possibly the first one that a properly situated sensor was running to catch when it arrived. This is the critical distinction that the entire expansion of the monitoring network makes plain. The instruments are not creating bigger waves. The ocean's violence is not increasing because scientists have built more tools to see it. What the tools are doing is revealing, with increasing reliability, a wave envelope that was always there. Extreme events occurring with a frequency the old frameworks could not accommodate, and that human observers, scattered across the surface of a vast ocean, in ships with limited sightlines and survival instincts that understandably prioritize seamanship over measurement, had never been positioned to document consistently. Which means that when a satellite recorded something remarkable in December 2024, and when that record stood in an interesting relationship to what the Newfoundland buoy had captured 5 years earlier, The comparison was not a simple question of which wave was bigger. It was a question of what each measurement method can and cannot see. And understanding that distinction is exactly what the intervening decades of instrument development had prepared scientists to ask. On the night of September 8th, 2019, just after 2 in the morning local time, a buoy anchored roughly 2.5 kilometres off Porto Basque on the southwestern tip of Newfoundland was doing nothing remarkable. It was recording wave heights, as it always did, in the dark and the cold and the building chaos of a storm that had spent itself over the Atlantic and was now delivering its residual fury to the Canadian coast. The buoy had no awareness that what it was about to capture would sit, years later, at the outer edge of what ocean physics suggests is even possible. The storm was the remnant of Hurricane Dorian. Dorian had already made landfall in the Bahamas as a catastrophic Category 5 storm, had scraped along the North American coastline, and by the time it reached Newfoundland had formally lost its tropical characteristics, reclassified as post-tropical, which sounds like a demotion but is more accurately a transformation. Post-tropical systems can retain ferocious intensity while absorbing the structure of mid-latitude weather patterns, and that is precisely what Dorian did. The region around Porto Basque was experiencing hurricane-force wind gusts approaching 150 kilometers per hour, dramatically low atmospheric pressure, strong onshore winds pushing water against the coast, and amplified tidal conditions that raised the baseline sea level above normal. Each of these factors individually contributes to wave energy. Together, aligned as they were in the early hours of that September morning, they created the kind of concentrated energy environment that wave physics requires to push an individual sea state toward its theoretical ceiling. What the buoy recorded was a single wave, crest to trough, of 30.2 meters, just under 100 feet of water, rising and collapsing in a matter of seconds. It remains the tallest wind-generated wave ever documented by any instrument anchored at the ocean surface. It received, relative to its significance, almost no public attention. That last point is worth examining carefully, because it reveals something important about how ocean records are communicated, and how the language of extremes depends entirely on the context of measurement. In December 2024, the SWOT satellite, a joint mission between NASA and the French space agency CNES, recorded a wave of 19.7 meters in the Southern Ocean. Headlines around the world described it as the highest ocean wave ever measured from space, which is accurate. Several outlets described it without the qualifier as a record wave. That framing, while understandable, missed the more complicated truth sitting in the buoy archives from 5 years earlier. The 2019 Newfoundland wave is taller by more than 10 meters, so why did it generate less attention, and why does the comparison between the two measurements require such careful handling? The answer begins with what each instrument actually measures. A moored ocean buoy sits at a fixed position on the water's surface and records conditions continuously. Every wave, every minute, every hour, in an unbroken time series. When an extreme event passes through, the buoy is there for it. The 30.2 meter figure from Newfoundland represents the single highest individual wave recorded at that location during Dorian's passage, a direct crest-to-trough measurement of an actual water surface at the moment of its maximum excursion. There is no averaging involved. There is no inference from remote sensing. The sensor was in the water, it went up, and it came back down, and the amplitude of that motion was logged with an error margin of roughly 0.3 meters. A satellite operates on an entirely different logic. The SWOT mission produces significant wave height estimates, a statistical measure derived from the average height of the highest third of all waves in a given area at a given moment. Significant wave height is the standard metric for sea state characterization and 19.7 meters of significant wave height is genuinely extraordinary, representing an ocean so violent that the average of its highest waves approaches what buoy measurements only catch at their most extreme individual spikes. But a satellite crossing a patch of ocean captures a snapshot, not a continuous record. It was not over every stretch of storm-driven water at the precise instant that the tallest individual wave crested. Whatever was happening in the North Atlantic or the Southern Ocean at the moment satellites were not overhead went unmeasured from space regardless of its height. This is not a flaw in the satellite technology. It is an inherent structural difference between two fundamentally different observational approaches. A buoy trades spatial coverage for temporal completeness. A satellite trades temporal completeness for spatial reach across ocean basins no buoy network could ever cover comprehensively. Neither is superior in any absolute sense. Each is better suited to different questions. But when those two measurement approaches produce numbers that get placed next to each other, in public discourse without their methodological differences being clearly explained, the result is precisely the kind of confusion that makes it genuinely difficult to answer the deceptively simple question of how big waves actually get. What makes the Newfoundland measurement particularly striking is not just its height, but its relationship to the theoretical limit of what the physics allows. Wave stability in deep water is governed by the Miescher criterion, which caps the steepness, the ratio of wave height to wavelength, at approximately 0.142. A wave attempting to exceed that ratio becomes too steep to sustain itself and breaks, dissipating its energy rather than continuing to build. Working through the mathematics for typical deep water wavelengths in a fully developed storm sea, that steepness limit translates to a practical ceiling for individual wind-generated wave height of approximately 30 meters. Not 50 meters, not 100 meters, about 30. The Newfoundland buoy recorded 30.2 meters. That single number sits right at the edge of what the physics of wind-generated waves permits. It is not a coincidence that the record approaches the theoretical limit rather than some arbitrary fraction of it. The conditions that produced it, extreme winds, sustained fetch, low pressure, tidal amplification, the residual energy structure of a major hurricane concentrated by post-tropical dynamics, were as close to optimal for producing a maximum height wave as natural conditions in the North Atlantic are likely to get. What the buoy caught was not just a large wave. It was a wave that had used up nearly all the room that ocean physics makes available. Whether any natural wind-generated wave has ever exceeded 30 meters and simply gone unmeasured is a question without a definitive answer. The monitoring record is good but not omniscient. Buoys can only be where buoys are. What the Newfoundland measurement does, however, is provide a calibration point. A real-world event that aligns so closely with the theoretical maximum that it transforms that maximum from an abstract calculation into a demonstrated empirical ceiling. The math said approximately 30 meters. The ocean, on a dark September morning off the coast of Canada, delivered exactly that. The question of whether any instrument will ever catch something larger depends on whether conditions can meaningfully exceed what Dorian produced on that coastline on that night, and on whether a calibrated sensor happens to be there when they do. So, if a buoy anchored off Newfoundland can capture a 30.2 meter wave at the precise moment it crests and collapses, the obvious follow-up question is this: what does the ocean look like when you step back far enough to see all of it at once? On December 21st, 2024, a satellite called SWOT, Surface Water and Ocean Topography, a joint mission between NASA and the French space agency CNES, passed over the North Pacific during a violent storm system that meteorologists had named Storm Eddy. What SWOT recorded there was a significant wave height of 19.7 meters, roughly 65 feet. It was immediately recognized as the largest ocean wave ever measured from space. The record held up under scrutiny, was reported in scientific literature, and made headlines in outlets that cover neither oceanography nor satellite engineering on any ordinary news day. The number is, on its face, smaller than what the Newfoundland buoy caught 5 years earlier by more than 10 meters, and yet the SWOT measurement represents something the Newfoundland measurement cannot, a fundamentally different kind of seeing, one that changes not just the scale of individual observations, but the entire architecture of how humanity monitors what the ocean is doing at any given moment. SWOT launched on December 16, 2022. Its design combines traditional radar altimetry with a wide imaging swathe that extends roughly 50 kilometers on each side of the satellite's orbital track, producing two-dimensional maps of the sea surface at a resolution of 250 meters. It can detect swells with amplitudes as small as 3 centimeters and resolve wavelengths stretching up to approximately 1,400 meters. That combination of sensitivity and breadth has no precedent in ocean observation from orbit. Previous satellite altimeters worked by firing a narrow radar pulse straight down and reading the return signal from a single point beneath the spacecraft. SWOT effectively replaced that narrow beam with a wide-angle portrait of the sea state across a swath of ocean that no buoy network could cover with equivalent resolution. What that portrait showed on December 21 was an ocean in extraordinary distress. The 19.7-meter figure is expressed as significant wave height, the average height of the highest one-third of all waves across the observed area during the measurement interval. That definition matters. It is not a single wave caught at its maximum excursion. It is a statistical characterization of a sea state so violent that its upper tier of waves averages nearly 20 meters in height. For context, a significant wave height of 12 meters is considered severe enough to compromise the structural integrity of vessels not specifically designed for extreme seas. At 19.7 meters of significant wave height, the ocean beneath SWOT's instrument on that December morning was not in a category that lends itself to casual description. The fact that this number is lower than the Newfoundland buoy's 30.2-meter individual wave measurement is not a contradiction. It is the most direct possible illustration of why measurement categories exist in the first place and why conflating them produces confusion rather than clarity. The buoy off Porto Basque recorded the single tallest individual wave in the continuous instrumental record. One wave, one moment, one sensor in the water. SWOT recorded the highest significant wave height ever captured by a spacecraft, a spatial average across a broad ocean segment derived from orbital geometry and radar physics. These are measurements of different things. A comparison between them is meaningful only when the methodological gulf between them is held in view. Within its own category, orbital measurement of significant wave height, the 19.7-meter figure from SWOT has no equal in the record. That makes it historic regardless of the larger number sitting in the buoy archive. There is another layer to what makes the SWOT observation significant, one that goes beyond the height figure itself. Using data from that single storm, scientists were able to track the wave energy generated by Storm Eddy across a journey of approximately 24,000 kilometers, from its origin in the North Pacific through the Drake Passage between South America and Antarctica and continuing into the Atlantic. The storm's own center was long gone by the time its wave energy reached those remote latitudes. What SWOT detected were what researchers described as wave echoes, swell trains propagating far beyond their source, carrying the kinetic signature of a North Pacific storm into ocean regions where nothing about local weather conditions would suggest any such event was underway. This is where orbital observation reveals something that no buoy array and no ship's crew could independently document. A vessel encountering heavy seas in the Drake Passage on a day of relatively moderate local wind conditions, might have no obvious explanation for the swells battering it from an unexpected direction. There would be no storm overhead, no atmospheric pressure anomaly immediately apparent, no meteorological cause visible within the horizon. But from orbit the causal chain is traceable. A storm that began thousands of kilometers away and weeks earlier, radiating energy outward in organized wave trains that maintained coherence across an ocean basin. The satellite does not just measure the wave, it provides the context for understanding where that wave came from and where its energy is going. That capacity changes the scope of what ocean scientists can monitor globally. A buoy delivers an extraordinary depth of temporal data about one location. It records every wave, every minute, for years. Its continuity is irreplaceable for understanding local wave climate and for catching extreme individual events in the manner that the Newfoundland record illustrates so dramatically. But there are approximately 1,300 operational wave measuring buoys distributed across the world's oceans, a number that sounds substantial until placed against the total surface area of approximately 360 million square kilometers of open water. The vast majority of what the ocean does happens in regions with no sensor anywhere near it. Storms rage in the Southern Ocean, in remote stretches of the Pacific, in the Arctic during polar winter, without any fixed instrument recording what they produce. Whatever individual waves crested in those regions went unmeasured, their heights unknown, their existence inferred only from model outputs and satellite passes that may or may not have been timed correctly. The uncertainty built into the SWOT measurement reflects this honestly. The 19.7 meter figure carries an error margin of approximately 0.3 meters, and researchers note that because satellite tracks are geometrically constrained, SWOT may have been over storm eddy at a moment that was not its absolute peak. The true maximum significant wave height of that storm may have been somewhat higher than what the instrument recorded. Satellite observation of extremes is subject to a timing problem that buoys, sitting continuously in the water, do not face, but the inverse is equally true. The buoy off Newfoundland was there because someone decided to anchor it there decades ago. Its coverage ends at the edge of its mooring cable. Storm eddy in the North Pacific on December 21st, 2024 had no buoy beneath it. The only instrument that saw it was orbiting 890 kilometers overhead, moving at 7 kilometers per second, tracing a path across the storm's wave field and capturing in minutes what no fixed sensor will ever record in that particular stretch of ocean. Between these two instruments, one in the water, one in orbit, the outlines of what the ocean is actually capable of are slowly becoming legible. So now we have the measurements. We have the records. A buoy catching 30.2 meters off Newfoundland. A satellite mapping 19.7 meters of significant wave height from orbit. A laser sensor on a North Sea platform recording the Draupner wave in 1995. And the natural next question is the one sailors have been asking in increasingly desperate language for centuries. Where do these things come from? The answer is not supernatural. It is not random. And it is not, despite the word that stuck to these events in the scientific literature, particularly freakish. Rogue waves, individual waves that tower at least twice the significant wave height of the surrounding sea, are statistically rare but physically inevitable. Understanding why requires a short trip into how ordinary ocean waves actually behave when they meet each other. Wind generates waves by transferring energy into the ocean's surface across broad stretches of open water. What results is not a single orderly procession of identical crests moving in lockstep. It is a chaotic spectrum of waves with different heights, different wavelengths, different speeds, propagating across the same water simultaneously. Longer waves travel faster than shorter ones. Wave groups of similar frequencies tend to cluster and then disperse as faster waves outpace slower ones. Under normal conditions, this creates what sailors describe as a confused sea, irregular, lumpy, unpredictable in detail, but broadly characterized by that statistical measure of significant wave height. Now imagine two of those wave groups arriving at the same location at the same moment, their crests aligned. The heights do not average out, they add together. This is constructive interference, and it is the core mechanism behind rogue wave formation. When multiple wave trains happen to arrive in phase, when crest meets crest rather than crest meeting trough, the combined wave is dramatically taller than any of its components. The surrounding sea looks much as it did before. The rogue wave appears not because conditions have changed, but because the geometry of timing briefly aligned in one specific location. Linear wave physics alone predicts this can happen, but research from Georgia Tech and others has shown that the reality is worse than the linear model suggests. Second-order non-linear effects, the way wave crests interact and steepen as they combine, mean that the actual crest height exceeds what a simple addition of component waves would calculate. The combined wave is not just tall, it is disproportionately steep, rising faster and more sharply than linear theory predicts. That steepness is part of what makes rogue waves so dangerous, and part of why they are so difficult to survive structurally. The wave that hits a ship in a rogue event is not just high, it is sharp, arriving with an almost vertical face that bears almost no resemblance to the long rolling swells a vessel is designed to handle. Currents and seafloor geometry amplify this probability further, and the effect is not subtle. When waves travelling against an opposing current, like the Agulhas current off the southeastern coast of South Africa, long notorious among sailors, their wavelengths shorten and their energy compresses. A wave group that was spread out and manageable becomes compact and dangerous. The probability that multiple components arrive in phase in the same spot increases sharply under these conditions. This is why statistically significant rogue wave clustering has been documented near major ocean currents, why the waters south of Africa feature so prominently in historical accounts of ships meeting walls of water with no warning, and why the oceanographic literature treats opposing current zones as natural amplifiers of the extreme. Abrupt changes in seafloor depth produce a related effect. When a wave train crosses from deep water onto a shallower bank or ridge, its velocity drops, its wavelength shortens, and its height increases to conserve energy. Wave groups following slightly different paths can be refracted by these features in ways that direct multiple trains toward a single convergence point, a process called bathymetric focusing. The result looks, from the ocean surface, exactly like a rogue wave appearing from nowhere, because the cause is underwater, invisible, operating on time scales and spatial scales that no observer on the surface can directly perceive. What all of this produces is a wave that behaves nothing like the surrounding sea state. Regular storm waves arrive in sets. Sailors learn to read their rhythm, count the waves, identify the larger sets within a swell pattern, and time their movements accordingly. A rogue wave does none of that. It rises out of a sea that may look merely rough rather than extreme, its height often more than twice the significant wave height of everything around it, its face nearly vertical, its arrival uncorrelated with any pattern the crew has been observing for hours or days. It is not that it arrives without warning signs. It is that its warning signs are written in the physics of the ocean beneath the surface, not in anything visible from a ship's bridge. How rare is rare? Probability models vary depending on assumptions about spectral shape, current interactions, and whether you're working from Rayleigh statistics or second-order corrections, but estimates generally place the occurrence of a true rogue event, a wave at least twice the significant wave height, somewhere in the range of 1 in 10,000 to 1 in 100,000 individual waves. In a violent sea generating thousands of waves per day over a broad area, that rarity does not translate to never. It translates to infrequently enough that no single vessel will encounter one routinely, but frequently enough across the global ocean that the cumulative risk to ships and offshore structures over time is real and documented. That is the uncomfortable mathematics at the core of offshore engineering. A platform like Draupner was designed using wave statistics from the surrounding North Sea, the best available data at the time. The Draupner wave of January 1, 1995 exceeded the design threshold not because the engineers made an error, but because the statistics they used did not adequately capture the tail of the distribution. Rogue waves exist in that tail, and the tail is heavier than the simpler models predicted. Every fixed offshore structure, every cargo vessel, every passenger ship operating in open ocean is operating within a probability envelope that includes, somewhere in its distribution, a wave it was not fully designed to survive. The measurements we now have, Draupner, Newfoundland, the clustering near the Agulhas, are not curiosities. They are the evidence base from which those envelopes need to be recalculated. The ocean does not announce what it is about to do. The rogue wave does not build gradually from the horizon, giving time for adjustment. It appears, fully formed, from a sea that looked like it was already telling you everything it knew. It was not. So the ocean does not announce itself. And now the question that has been underneath this entire video from the first frame: if one of these waves finds you, can you live through it? The honest answer is that it depends entirely on where you're standing when it arrives. Inside a ship is not the same as inside the water. On a surfboard is not the same as inside a ship. The wave does not change. The human situation changes everything. A 25-meter wall of water moving at speed carries roughly the same energy, regardless of whether it finds a cargo vessel, a cruise liner, or a person in a wetsuit. What varies is the interface, what stands between that energy and a human body, and how much time exists between impact and rescue. Start with the clearest case. In 2024, the Norwegian cruise liner MS Maud was struck by a rogue wave in open ocean. The wave killed the ship's navigation system. It was violent enough to do structural damage to electronics and systems that cost millions to replace. On board were 266 guests and 131 crew, 397 people, and every single one of them survived without physical injury. The ship's emergency systems engaged. Nearby rescue vessels were on standby. The hull absorbed the blow. The people inside experienced something catastrophic and walked away from it, not because rogue waves are survivable in some general sense, but because a modern ship is a survival structure. It is designed to take impact, manage flooding, and keep people separated from the water trying to reach them. That separation is the key variable. Remove it. Put a person in the water instead of inside a vessel, and the same wave becomes something categorically different. In seawater around 10 to 16 degrees Celsius, which covers much of the North Atlantic where the largest rogue events have been recorded, exhaustion sets in after roughly 1 to 2 hours of immersion. Death from hypothermia typically follows within 2 to 7 hours, and those are averages. Without flotation, the timeline compresses dramatically. Without rapid rescue, flotation alone is not enough. A person who survives the initial impact of a rogue wave, but ends up in cold, open ocean, without immediate extraction, is not surviving a wave. They are surviving a clock, and the clock runs fast. So when people ask whether a human being can survive the biggest waves ever recorded, the question has to be split into pieces. Survive the impact inside a structurally sound vessel? Yes, the MS Maud is proof. Survive open water immersion in the same event? That is a different calculation entirely, governed by temperature, flotation, and how quickly someone reaches you. Then there is the third context, the one that seems most improbable, but has generated the most documented evidence of human survival at extreme wave heights: big wave surfing. Here the physics of survival works differently, because the surfer is not trying to resist the wave. They're trying to move with it, to use its geometry rather than absorb its force. Angle matters enormously. A wave ridden at a controlled diagonal across its face produces one outcome. A wave that breaks vertically onto a stationary person produces something close to the opposite. In 2011, Garrett McNamara rode an estimated 90-foot wave off Nazaré in Portugal and survived. In the aftermath, he credited mental rehearsal, methodical safety preparation, and what he described simply as the grace of God. Those three factors, while they don't map neatly onto a physics equation, describe something real. The preparation reduced the variables he could control, and the luck governed the ones he could not. The wave broke where he needed it to. The trajectory held. He stayed on the board. When he did not, the rescue team reached him before the next set. That rescue infrastructure is the part the footage does not always capture. What the cameras show is a surfer on a wall of water. What the cameras do not always show are the jet skis positioned at the channel, the safety swimmers with flotation sleds, the coordinated communication between the team on the water and observers on the cliff. Big wave surfing at the elite level is not an individual act of recklessness. It is a logistical operation built around the assumption that the surfer will eventually be in the water and will need to be extracted from it within seconds, not minutes. Laird Hamilton's rescue of Brett Lickle after an 80-foot wipeout off Maui illustrates the stakes when that system is stressed. Lickle was badly injured. Hamilton improvised a tourniquet from clothing, then swam half a mile through the same sea to retrieve their watercraft and complete the evacuation. The survival was real. So was the margin. A few different choices, a slightly different breakpoint on the wave, a few more minutes in the water, and the outcome changes. This is what makes the survival question so difficult to answer with a clean yes or no. The same wave height, call it 25 meters, is survivable in one context, lethal in another, and everything in between depending on angle, preparation, flotation, rescue speed, and a category of variable that professionals in this space do not minimize or dismiss. Luck. The wave breaks slightly differently. The rider's line is slightly off. The rescue sled is 30 seconds further away. These are not dramatic failures. They are tiny shifts in a system with very little margin, and at the extreme end of wave height, the margin is the difference between a story told on camera and a name added to a list. What emerges from looking at every documented survival, the MS Maud, McNamara at Nazaré, Hamilton off Maui, the long history of ships that absorbed rogue wave strikes and reported them in the maritime records, is a consistent pattern. Survival is not random. It correlates strongly with separation from the water, with preparation, with redundant rescue systems, and with the specifics of how the wave's energy is transferred to whatever it finds. But it also correlates with something that cannot be engineered or drilled or planned around. The ocean has its own variables and it does not share them in advance. The people who have survived the biggest waves are not the people who convinced themselves the waves were manageable. They are the people who understood exactly how dangerous the waves were, prepared accordingly, and then accepted that they were still leaving something to chance. Two groups of people have done this at the absolute frontier: the surfers who have chosen to seek these waves out deliberately, and the sailors who have met them without any choice at all. The surfers represent something distinct in the entire history of human encounters with extreme water. Everyone else in this story, the sailors on the Draupner platform, the passengers aboard the MS Maud, the crews of freighters that met rogue walls in the middle of the night, arrived at their moment with the ocean without asking for it. The big wave surfer is the only person in the record books who looked at a 25-meter wall of moving water and decided to go find one. That choice changes the nature of the encounter in ways that matter, because what elite big wave surfing actually is, stripped of the footage and the mythology, is a logistical operation designed to convert a potentially lethal event into a survivable one. The wave is not tamed. The ocean does not cooperate. But the human side of the equation is engineered to the point where variables that would kill an unprepared person are anticipated, rehearsed, and covered by redundant systems before anyone enters the water. Start with the most basic problem. The largest waves in the world move too fast to catch by paddling. A surfer trying to match the speed of a 20-metre swell by hand would never get onto it at all. This is the problem Laird Hamilton and a small group of surfers solved in the mid-1990s when they developed tow-in surfing. The concept is straightforward. A jet ski tows the surfer on a rope into position, accelerating them to the wave speed before releasing them onto the face. The rider is placed precisely where the geometry of the wave is rideable, moving fast enough to hold a line. What Hamilton and his collaborators unlocked was not just bigger waves. It was the practical methodology that made any of what followed possible. Without tow-in, the surfable size ceiling stays well below what the ocean is capable of generating. With it, the ceiling becomes a question of nerve and preparation rather than physics. The safety architecture built around that methodology is what makes survival possible when things go wrong. And at this scale, things go wrong regularly. The same jet skis that deliver surfers to the wave face are stationed at the channel during every ride, crewed by experienced water safety operators watching every movement. The moment a surfer wipes out, the clock starts. The goal is extraction within seconds, not minutes, because in heavy surf the next wave in the set arrives fast, and a person held underwater through 2 or 3 consecutive impacts is in serious physiological danger. Helmets, inflation vests, and flotation sleds are standard. Communication between water crew and observers on land is continuous. This is not a sport where individuals paddle out alone. At the professional level, it functions more like a coordinated rescue operation that happens to have someone surfing in the middle of it. Garrett McNamara was among the figures who brought this infrastructure to Nazaré, a canyon-fed break off the Portuguese coast that has produced some of the most extreme surf ever documented. In November 2011, McNamara rode a wave there that was independently measured at approximately 78 feet, around 24 metres, earning a Guinness World Record that stood for over a decade. Nazaré works the way it does because of an underwater canyon that funnels and amplifies Atlantic swells before they reach the shoreline, stacking energy that would dissipate elsewhere into concentrated walls of moving water. McNamara did not stumble onto the spot. He spent years developing local knowledge of the canyon's behaviour, the specific way the swell refracts and peaks, and the windows within a session when the waves are readable versus when they are simply dangerous. That local knowledge is not incidental. At wave heights where margins are measured in fractions of a second, knowing where the wave will peak, how fast it will stand up, and where the channel offers safe water for extraction is the difference between a record ride and a catastrophic hold down. Big wave surfing at these scales rewards the surfer who has studied a spot obsessively over the one who simply has the most physical ability. The wave's geometry is predictable within limits. What varies is the swell period, the wind, the tide, and reading those variables accurately before paddling out is a form of expertise that takes years to develop at a specific location. Which brings the story to February 24th, 2024, and the current frontier. Sebastian Steutner, a German big wave surfer who has spent years working specifically with engineering teams to advance safety and measurement technology, rode a wave at Nazaré that was measured at 28.57 metres, just under 94 feet. The measurement was made by a custom Porsche engineering drone that tracked both Steutner and the wave simultaneously, capturing crest to trough height with centimetre scale precision. The World Surf League has not yet formally ratified the record, but the claim represents the leading edge of documented human performance in extreme surf. The drone is worth pausing on because it marks a genuine methodological shift. For most of big wave surfing's history, wave heights were estimated visually, by observers on cliffs, by panels of expert surfers, by reference points in video footage. These methods produced usable approximations but introduced significant uncertainty, particularly at the upper end where small perceptual errors translate to large differences in claimed height. Photogrammetric drone mapping eliminates much of that uncertainty by constructing a precise three-dimensional model of the wave from above, providing a measurement grounded in geometry rather than estimation. There is a caveat that matters here, and it runs through every comparison between surfing records and oceanographic data. The height reported in a surf record describes the surfable face, the portion of the wave that a rider actually traverses, which is roughly the steep front face from the crest to the base. Oceanography defines wave height as the full crest to trough vertical distance, which includes geometry below the still waterline and typically runs 10 to 15% larger than the surfable face alone. When Stütner's 28.57-metre ride is placed next to the 30.2-metre buoy, reading recorded off Newfoundland in 2019, the numbers are close, but they are measuring different things by different methods with different instrumentation. They are not directly comparable without accounting for those definitions, and collapsing them into a single ranking produces a misleading picture. Drone mapping is more rigorous than what came before it, and it moves surf records toward a more defensible scientific footing, but it is still being standardized. The protocol for what exactly is measured, how the drone is positioned, how the data is processed, and how independent verification is conducted has not yet been unified across the sport's governing bodies. Stütner's record is a claim pending ratification precisely because those verification steps are still in process. The measurement itself may well be accurate. The institutional machinery for confirming it officially is still being built. What all of this adds up to is a portrait of people who are not reckless, but who have chosen to operate at a threshold where the gap between survival and catastrophe is genuinely narrow, and who have built elaborate systems to manage that gap without pretending it does not exist. They have compressed the randomness as far as preparation can compress it. They ride the largest waves any human being has ridden, and they understand with full clarity that the systems they have built are good, and that they are not perfect. The surfers who chase Nazare have built their survival around speed, skill, and a small team of people on jet skis watching every move. What they do not have is steel. They do not have watertight compartments, redundant power systems, or a hull engineered to absorb forces that would otherwise be catastrophic. That distinction between a person on a board and a ship turns out to reveal something fundamental about what rogue waves actually do and what it takes to walk away from one. On December the 21st, 2023, the Norwegian cruise liner MS Maud was crossing the North Sea when a rogue wave struck the vessel. Aboard were approximately 266 guests and 131 crew, close to 400 people in total. Not one of them was injured. That outcome sounds like the headline, but what happened to the ship in the minutes that followed tells the more instructive story. Water entered the bridge. Not metaphorically, physically, water forced its way into the electronics that run a modern vessel's navigation and radar systems, and those systems went down. The MS Maud was left manoeuvrable only through emergency backup systems. A vessel carrying nearly 400 people, struck by a wave whose exact height was never officially disclosed, was suddenly operating with degraded situational awareness in one of the world's busiest and most unpredictable bodies of water. Everyone was alive, the ship could move, and that is where the margin between survival and disaster was sitting. This is what rogue waves do to ships, even when the outcome is, by any reasonable measure, good. They do not always sink vessels outright. They disable them. They compromise the systems that allow a crew to understand where they are, what is around them, and what is coming next. A crippled ship in confused seas is not a safe ship. It is a ship that has used up a large portion of its reserve capacity, and now has less left to meet whatever follows. The no-injury figure from the MS Maud is real, and it matters. It should not be read as evidence that rogue waves are manageable threats that modern ships absorb without consequence. The bridge electronics said otherwise. What actually determines whether a vessel survives a rogue wave impact comes down to 4 interlocking factors, and each one was relevant in the Maud's case, whether or not the crew had time to act on all of them. The first is heading. When a rogue wave appears, the geometry of the encounter matters enormously. A ship meeting a wave bow first uses the strongest section of its hull, the reinforced bow, to absorb the initial impact and allows the wave energy to distribute along the vessel's length, rather than striking a flat broadside surface. Captains who have warning time will steer toward the wave or angle toward its shoulder, where the face is less vertical and the energy slightly less concentrated. The problem is that warning time is often measured in seconds. Rogue waves are not forecast. They appear without the telltale build-up of a normal swell sequence, which means a crew acting on instinct and immediate observation rather than meteorological prediction. The second factor is hull strength. Modern commercial vessels are built from high-strength steel with transverse framing. Double hulls in critical sections and watertight compartments designed to contain flooding and prevent cascading structural failure. This architecture exists precisely because the forces involved are not theoretical. Research from the Institute of Marine Engineering, Science and Technology has estimated that rogue waves can exert pressure of approximately 100 tons per square metre. Ships are typically designed to withstand around 15 tons per square metre. That is not a small gap. It is a gap that hull engineering attempts to close through redundancy, load distribution, and structural reserve, not through a direct match between design strength and wave force. When a rogue wave hits, the hull is absorbing forces it was never explicitly designed to handle. That it usually succeeds is a testament to conservative engineering practices and safety margins built into the original specifications. That it occasionally fails entirely is a testament to the same physics. The third factor is bridge exposure. The MS Maud's outcome showed this with unusual clarity. Navigation systems, radar, electronic chart displays, communications equipment, all of it is centralized in the bridge, which sits high on the superstructure and is therefore exposed to spray, impact water, and green water that makes it onto the upper decks. Redundancy and sealed bridge enclosures are not luxuries in this context. They are the difference between a ship that loses some electronics and a ship that loses its ability to navigate. Modern design increasingly treats bridge waterproofing as a structural priority rather than an aesthetic one, but the Maud incident is a reminder of how quickly that protection can matter. The fourth factor is warning time, and it interacts with all 3 of the others. Weather routing services, satellite sea state data, and onboard monitoring systems give a crew their best possible chance of identifying anomalous wave conditions before they arrive. In practice, many rogue wave encounters still occur with minutes of notice or less, and some occur with none. The crew of the MS Maud may have had moments to react, or they may have had none. The publicly available reporting does not specify. What is clear is that the outcome depended on what was already true about the ship, its hull, its heading at the moment of impact, and the degree to which its critical systems could absorb what came through. None of this carries the visual drama of a surfer dropping down a 28-metre face. Ship survival is institutional, distributed, anonymous, the result of engineers who never met the passengers and designers who worked from statistical worst-case assumptions rather than lived experience. There is no footage that captures a crew member maintaining composure at the wheel while a wall of water arrives at the bow, partly because the people involved are professionals trained not to make that look cinematic. But the information encoded in what the MS Maud survived, and in what it lost in the process, is at least as revealing about wave power as anything from Nazaré. Possibly more so, because it shows the edge of what structured engineering can do and where that edge sits. That edge is considerably further out than where an individual in open water stands. The surfers at Nazaré have built an impressive safety architecture around their work, and it is genuinely good. But they do not have steel. A person caught in open water by a rogue wave, without a vessel, without a team, without an inflation vest, is operating at a margin that makes the Maud's experience look comfortable. The ship survived with its 400 people intact and its bridge temporarily dark. A person alone in that same water, in that same moment, faces a categorically different set of odds. What protects you in the ocean, it turns out, is almost always something built before you arrived. Everything discussed so far, the Draupner platform, the Newfoundland buoy record, the SWAT satellite measurement, the surfers at Nazaré, the MS Maud and its darkened bridge, belongs to the same physical category. Wind energy transferred to water, focused by bathymetry or constructive interference, eventually breaking under its own steepness. The Mischie criterion gives that category a ceiling of roughly 30 meters for open ocean waves, and the data collected across decades of instrumented measurement has never convincingly broken through that ceiling. Within that world, the records are impressive. They are also, in a sense, bounded. Then there is Lituya Bay. On the evening of July 9th, 1958, a magnitude 7.8 earthquake struck the Fairweather Fault in southeastern Alaska. The shaking was powerful enough to trigger a catastrophic rock and ice slide at the head of the bay. Approximately 90 million tons of material that fell from a height of roughly 900 meters and hit the water in a single, near-instantaneous displacement. What happened next produced the largest wave ever recorded in human history, and it had nothing to do with wind. The rock didn't generate a wave the way a storm does. It didn't transfer energy gradually across hundreds of miles of open ocean, building a swell that steepens as it approaches shallow water. It displaced the water. All of it, at once, in a confined space. The bay's geometry did the rest. Lituya Bay is a narrow, T-shaped fjord on Alaska's Gulf Coast, with steep rock walls rising sharply on both sides, and an enclosed head that acts almost like a bowl. When 90 million tons of material hit the water at the head of that bowl, the water had nowhere to go but up. The wave that resulted had a measured run-up height of approximately 524 meters, roughly 1,720 feet. That is taller than the Empire State Building. It is more than 17 times the height of the MS Maud's wave. It stripped forest from the hillsides to a line 524 meters above sea level, leaving a bare scar in the landscape that aerial photographs documented in precise geometric detail. That 524-meter figure requires a careful clarification, and it matters for how you understand the event. This is a run-up height, not a crest-to-trough measurement of a wave on open water. Run-up is the vertical elevation that water reaches when it climbs a surface. In this case, the rocky slopes of the bay's walls. The wave itself, as it crossed the water, was not 524 meters tall in the sense that a surfer might face a 28-meter wall. What the number tells you is how high the water travelled after impact, which reflects both the wave's enormous energy and the particular geometry of the terrain it hit. That distinction doesn't make the number smaller in any meaningful human sense. A wall of water that strips trees from a hillside at the height of a skyscraper is not a phenomenon that ordinary wave physics can accommodate. But the distinction matters for comparison. 3 fishing boats were anchored in the bay that night. The crew of one of them, Howard Ulrich and his young son, watched the slide happen from their anchorage near the bay's mouth. The wave that reached them lifted their boat over the spit at the entrance to the bay and out toward the open Gulf of Alaska. They were carried above the treetops, looking down at forests below them, before the wave set them back down. They survived. The two people aboard a second boat were not as fortunate. Their vessel was swept and destroyed. A third boat also survived, its crew left shaken but alive, their account one of the only first-hand descriptions of a mega tsunami on record. What the Lituya Bay event teaches is not a refinement of what we know about waves, it is a lesson about categories. The physics that produced 524 meters of run-up are not an extreme version of the physics that produced the Draupner wave or the 30.2 meter buoy record off Newfoundland. They are different physics entirely. A mega tsunami, the technical term for a wave generated by sudden, massive displacement of material, doesn't require wind, fetch, or ocean swells. It requires a large mass moving very fast into a body of water. Landslides can do this. Volcanic collapses can do this. An asteroid impact can do this. In each case, the generation mechanism bypasses everything that caps ordinary wave height. The Misha steepness criterion is irrelevant. The relationship between wind speed and wave energy is irrelevant. The constraint that limits open ocean storm waves to roughly 30 meters simply doesn't apply, because none of those constraints are in operation. The confined geography of Lituya Bay amplified the event dramatically. A similar landslide into open ocean would still generate a wave of extraordinary violence, but without steep surrounding walls to reflect and funnel the energy, the run-up would be far lower. The bay acted as both a trap and an amplifier. Energy that in open water would have spread outward in all directions was instead channeled, bounced between walls, and directed upward along the slopes. This is why the mega tsunami literature emphasizes that run-up heights in enclosed settings cannot be generalized to open coastlines, and why the 524-meter figure, though real, represents a specific combination of landslide scale, impact geometry, and fjord topology that is unlikely to be replicated exactly anywhere else. None of this means the threat is negligible outside Alaska. The Canary Islands host volcanic slopes that researchers have long studied for potential collapse, and models suggest that a major flank failure there could generate mega tsunamis capable of crossing the Atlantic. The physics are well understood. The timing is not. What Lituya Bay provides, in the absence of more recent events of comparable scale, is empirical confirmation that the upper bound on wave height, when you step outside the wind-driven category, is not 30 meters. It is not even close to 30 meters. This is the careful answer to the script's central question. How big can waves actually get? It depends entirely on which kind of wave you're asking about. Within the domain of wind-generated ocean waves, the swells that surfers ride, the seas that ships navigate, the monsters that buoys measure in the North Atlantic, the practical ceiling sits around 30 meters, and the records cluster just below it. Step outside that domain, into the territory of sudden displacement events, and the ceiling disappears. 524 meters of run-up in a fjord in Alaska is not a bigger version of a rogue wave. It is a different thing, generated by different forces, shaped by different terrain, and survivable only by extraordinary luck and geography. Comparing Lituya Bay to Nazare, or to the Newfoundland buoy record, or to anything the SWAT satellite has captured, is a category error dressed up as a comparison. The numbers share no common denominator. What they share is the water. So the categories are established. Wind-driven waves with a physics-imposed ceiling around 30 meters, and displacement events that operate by entirely different rules. The records we have, buoy measurements, satellite snapshots, drone-mapped surf rides, platform sensors, cluster within that first category and press against its upper boundary without breaking through. That is where science stands right now. But the instruments are getting sharper. The data streams are getting denser and the models are getting smarter. What happens to our understanding of extreme waves when the tools improve? The honest answer is that better measurement tends to produce bigger numbers, at least initially. Not because the ocean is changing, but because we are finally watching closely enough to catch what was always there. Consider what has already shifted in just 3 decades. Before the Draupner wave in 1995, rogue waves, individual crests far exceeding the surrounding sea state, were widely treated as sailor mythology. A single instrumented measurement changed that. Within a decade, satellite altimeters scanning the global ocean confirmed that anomalous waves were not rare. They were common, appearing across all ocean basins in numbers that surprised researchers. The ocean hadn't changed. The observation network had. That trend is accelerating. Deep learning models applied to scatterometer data, including the ASCAT instrument that sweeps the global ocean continuously, can now produce significant wave height estimates with a root mean square error of roughly 0.5 meter. That sounds like a small number, but for a field where individual records have historically hinged on a few meters of uncertainty, it represents a meaningful tightening of the margins. When the SWAT satellite captured a 19.7 meter wave on December 21, 2024, the highest single wave ever measured from space, it was doing so with a spatial resolution that earlier altimeters couldn't approach. And yet, that number, 19.7 meters, still sits below the 30.2 meter buoy record off Newfoundland from September 2019. The gap between those two figures isn't a contradiction. It reflects a fundamental limitation of satellite observation. A satellite captures a wave at a single moment in its orbit. A buoy sitting in one place through the heart of a storm has time to find the peak. The same physics, 2 different windows onto it, producing 2 different numbers that are both accurate and both incomplete. The NISAR mission carrying dual-band synthetic aperture radar is designed to push further still. Centimetre-scale sea surface imaging that can reconstruct wave spectra and individual crest-to-trough heights from orbit. When that capability becomes routine, the record landscape will almost certainly shift again. New instruments will catch waves that no sensor was positioned to catch before. Whether those catches represent genuinely larger waves or simply better sampled waves is a question that will require careful interpretation. More observations mean more opportunities to find the upper tail of the distribution. That is not the same as the upper tail getting larger. The same logic applies to where extreme waves are most likely to occur. Climate projections and high emission scenarios suggest that 1 in 100-year significant wave heights could increase by up to 1.5 meters in several basins: the Western Pacific, Eastern Pacific, South Indian and South Pacific, by around 2050. Future modelled maxima for some of those basins reach 18 meters in the Western Pacific and around 16.9 meters in both the Eastern Pacific and North Atlantic. These are not small changes for coastal infrastructure and shipping, but they don't revise the underlying physics. Stronger and more persistent storms transfer more energy to the water surface, and that produces larger waves. The Misha steepness limit doesn't care about emission pathways. It is a geometric constraint on wave shape, not a climate variable. What shifts under warming is the distribution, where the largest waves appear most often, how frequently the upper tail is reached, and which ocean basins become the new hotspots for extreme sea states. The ceiling stays where it is. The frequency of approach changes. This matters for how we think about official records, because record keeping depends on where instruments happen to be when history is made. The North Atlantic has been the traditional centre of gravity for extreme wave science, partly because of its fierce winter storms, and partly because decades of platform-based measurements, like Draupner and high-density buoy networks, created a concentration of data there that other basins lacked. If warming shifts the most extreme seas toward the Western Pacific or South Indian Ocean, and those regions simultaneously receive denser instrument coverage, the record books will reflect that shift. The physics won't have changed. The observation geometry will have. On the surfing side, official standards are catching up to the technology more visibly. Sebastian Steudtner's 28.57-metre ride at Nazaré in February 2024, measured by drone photogrammetry and awaiting formal ratification, represents the practical frontier of what a human being has verifiably ridden on a wind-driven wave. Drone-based measurement is more precise than the visual and photographic estimation methods that governed record claims for decades, producing sub-metre accuracy where earlier methods carried uncertainties of several metres. But standardization across different drone systems, different mapping algorithms, and different definitions of what counts as the wave height at the moment of riding, leading edge, trailing face, steepest point, is still being worked out. The records are real. The methodology is still maturing. That combination means official figures will continue to shift even in periods when the ocean itself isn't producing anything historically unusual. What all of this converges on is a distinction worth holding clearly in mind. There is the physics limit, the approximately 30-metre ceiling that deep water wave steepness imposes on wind-generated swells before they collapse under their own geometry. That number is stable. It has not changed because our instruments improved, and it will not change because our satellites get sharper or our AI models get better. And then there are the records, the highest values ever captured by a specific instrument at a specific time and place. Those will keep moving because the global ocean is enormous. The events that produce extreme waves are relatively rare, and we have only been watching carefully for a few decades. More eyes on more water will find more extremes, right up to and approaching the physical ceiling. And then, separate from both, there are events like Lituya Bay. No amount of improved satellite coverage or AI-processed scatterometer data will bring mega tsunamis within the same framework as wind waves, because they don't belong there. The future of wave science will sharpen our picture of the wind-driven category considerably. It will not shrink the gap between that category and a 524-metre run-up in an Alaskan fjord. Which returns the question to the human scale, because ultimately when people ask how big waves can get, what they are often really asking is whether those waves can be survived, and here is where category and context do more work than raw height. A 30-metre rogue wave in the open North Atlantic striking an unprepared vessel broadside is a catastrophic event. The same height at Nazaré, approached by a prepared surfer on a towboard, with a safety team in the water, has been ridden and survived. The MS Maud's crew lived through a rogue wave that disabled their navigation system and left them in darkness. Howard Ulrich and his son were carried over the treetops at Lituya Bay and set back down in the open Gulf of Alaska. Survival at the extreme edge of wave physics has always depended less on the number itself than on preparation, geometry, luck, and the specific way the water finds you. The instruments will keep improving, the records will keep moving, the physics will stay where they are, and the ocean will keep reminding anyone who pays close attention that the boundary between the measurable and the survivable is not a fixed line. So here is the answer, assembled from everything the ocean has shown us. For wind-generated waves in deep water, the practical ceiling is around 30 metres. That number comes from geometry, not guesswork. The Miche criterion sets the steepness limit at roughly 1 unit of height for every 7 of length, and beyond that ratio a wave collapses under its own weight before it can grow taller. Physics enforces the boundary, and the boundary holds regardless of how severe the storm is or how long the wind blows. Energy above the threshold goes into braking, not building. 30 metres is where the math runs out. The measurements we have gathered cluster right beneath that ceiling and press against it without punching through. In January 1995, the Draupner platform recorded 25.6 metres during a North Sea storm. The the first instrumented proof that rogue waves were real, not rumour. In September 2019, a buoy sitting in the path of post-tropical Storm Dorian off the coast of Newfoundland logged a single wave at 30.2 metres, the highest wind-generated wave ever captured by a continuous in-situ sensor. In December 2024, the SWAT satellite photographed a 19.7-metre crest from orbit, lower than the buoy record, not because the ocean was calmer, but because a satellite crosses a given patch of water once, and a buoy stays through the entire storm. Each number is accurate, each reflects a different window onto the same phenomenon, and all of them land within the range that the physics already predicted. On the surfing side, Sebastian Draupner rode a wave at Nazaré in February 2024 that drone photogrammetry measured at 28.57 metres, just under 94 feet, pending official ratification and pressing the edge of what the human-ridden record has ever approached. The drone measurement is more precise than the visual and photographic methods that governed earlier claims, but the standards for that precision are still being finalised. The record is real. The number may yet shift slightly. What is not in doubt is that a person rode a wave within a few metres of the theoretical ceiling and survived to describe it. And then there is Lituya Bay, the 1958 landslide-triggered mega-tsunami that stripped trees to a height of 524 metres above the waterline belongs in its own category entirely. Not a wind wave, not a rogue wave, but a displacement event governed by geology rather than meteorology. It is the largest wave height ever recorded on Earth, and it has no relationship to the 30-metre ceiling for wind-driven swells. Comparing Lituya Bay to a North Atlantic storm wave is like comparing an avalanche to rainfall. Both involve water moving. Everything else is different. So can a person survive the biggest waves? The answer depends entirely on which category you mean and how you encounter it. Big wave surfers at Nazaré and Jaws have been riding 20 to 30 metre faces for years, with safety teams, jet skis and inflation vests designed specifically for the worst-case scenario. Studner, Laird Hamilton, Garrett McNamara. These are not people who stumbled into large water. They are athletes who built systems around surviving the thing they were chasing. When those systems work, the answer is yes. At sea, the MS Maud lost navigation power to a rogue wave in the North Sea in December 2023, and all 400 people aboard came through unharmed, a modern ship absorbing an impact that would have ended an older vessel. At Lituya Bay, Howard Ulrich and his son were swept over a forested hillside in their fishing boat and set down in open water, alive. Survival at extreme wave heights is possible. It has never been guaranteed, and it has never been only about the height. What changes going forward is not the ceiling, but our ability to see how often the ocean approaches it. The instruments are sharper now than they were in 1995, sharper now than they were in 2019, and they will be sharper still in 5 years. Better satellites, denser buoy networks, standardized drone mapping. All of it means that the records we hold today are probably not final. The ocean isn't growing. Our picture of it is. That leaves us with the image that sits at the centre of this entire question. A wall of water somewhere between 25 and 30 metres tall, building in the open North Atlantic or off the Portuguese coast, carrying enough energy to sink a ship or make a surfer famous. The line between those two outcomes is not drawn by the wave. It is drawn by everything that happens before the moment of contact, the preparation, the position, the geometry of the encounter, and the irreducible element of luck that no instrument has ever been built to measure. The ocean sets the ceiling. Everything below it is ours to navigate.